my friends, my viewers at home. I want to appreciate you guys for your likes, for your comments on my previous video. And today we're going to be taking on a very interesting topic in chemistry, which talks about thermodynamics, thermochemistry. So this aspect, we'll just talk about the theoretical aspect of it. Then afterward, we'll now move straight down to what to thermochemistry, and therefore we'll perform some calculations in them. Now, first of all, what is thermodynamics? Now, thermodynamics can be defined as the study of the relationship between heat and other forms of energy that are involved in all the types of chemical processes. Or we can also define it to be as the study of the flow of heat or any other forms of energy into or out of the system as it undergo both physical and chemical transformation. Now, your understanding of the major heading thermodynamics from the word is broken down into two: thermo, which is about heat, and dynamics, which is about a movement, a transformation. And we have established the fact of two major definitions of what we call thermodynamics. And we said that thermodynamics is the study of the relationship between heat and other forms of energy that are involved in all the types of chemical processes, or the study of the flow of heat or any other forms of energy into or out of the system as it undergoes a chemical or a physical transformation. Now there are some basic terms or terminology or basic thermodynamic concept that we should understand in regards to what we call thermodynamics. And that one, we'll talk about what we call the system, what we call the surrounding, also called the environment. Then lastly, what we call the boundary. Now, the question now is, what is a system? Now, it will interest you to know that a system is that part of the universe which is under under thermodynamic study. I repeat, I said a system is that part of the universe which is under thermodynamic study. They will then move to what we call a surrounding. A surrounding can also be called an environment. Now, a surrounding is the rest of the universe, or is the rest part of the universe outside the system. Then lastly, what we call boundary. Now what's the boundary? A boundary is a real or imaginary surface that separates both the system, or that separates the system from the surrounding. Now, a quick representation of what we talk about here, is that this part is called a system. We said that a system is that part of the universe that is under thermodynamic study. And this part here is the boundary. This is the boundary. Now, why this large part you are seeing here is what we call the surrounding. The surrounding. Now, we have said that this part here is called the system, which is under thermodynamic study. Why this boundary, which is an imaginary line, or which is a real surface, it separates the system from its surrounding or environment. Now we then move to what are the types of system we should know. Now, basically we have three types of system. The first one is what we call, an open system. What we call an open system. Second, what we call an isolated system. Then lastly, what we call a closed system. Now, when do we say or what do we mean when we say that a system is open? Now, a system is said to be open when there is an exchange of both matter and energy with its surrounding. I repeat, a system is said to be open when there is an exchange between matter and energy between its what now? Well, with its surrounding. They will then move to what we call an isolated system. A system is said to be isolated. It is the direct opposite of open. Now, a system is said to be isolated when there is no exchange of water, or when there is neither an exchange of matter and energy with its surrounding. A very good example is what we call the thermoflask. The thermoflask. When a boiling water is put in a thermoflask, because that water will remain hot depending on when you use it. Why? Because in a thermoflask, the way it was being made is that no heat, or there is no exchange of matter and energy between its with its surrounding. Then lastly, what we call a closed system. A system is said to be closed when there is only a transfer of energy but not matter. Exactly. And with that part that we now understood, we can then talk of what we call an homogeneous system and an heterogeneous system. Now, when you say a system is homogeneous, it means it contains one phase only. One phase is called from the word homogeneous system. The system contains just one phase. And when you say that a system is heterogeneous, it means that system contains two different phases. All right. Persona and extensive properties, which are the intensive properties, and what we call the extensive properties. Now, when do we say a property is intensive? Now, intensive properties are properties which does not depend on the quantity of matter present in the system. And a very good example of such properties are temperature, we have pressure, we have density, we have concentration. Now, it will interest you to know that intensive properties are addictive. You get me now? Now, the opposite of intensive properties are what now? Extensive property. Now, a property is said to be extensive when it does depend on the quantity of matter present in the system. A very good example we have volume, we have number of moles, we have enthalpy, we have entropy, we have free Gibbs energy. And take note that extensive properties are not addictive. Exactly. They will then move to what we call a thermodynamic process. Now the question now is, what is a process? Because the truth is, this aspect of chemistry need to be properly understood, so that all of that part can be so when we enter calculation, it will you understand it much more better. Now, what do we call a process to start with? Now, a process is when there is a thermodynamic change from one state to another. So we call that a process, meaning with the thermodynamic changes from one state to another. And these processes are 4 in number. We have the first one, what we call isothermal process, what we call isobaric process, what we call isochoric process, then lastly what we call adiabatic process. Now, firstly, when do we say a process is isothermal? Now, isothermal processes, they are processes in which the temperature remain what? Fixed. Or you can say that the temperature remain what? Constant. And by so doing, we can say that dt is equal to what now? 0, meaning the temperature is fixed. In the case of isobaric process, in isobaric process, the pressure is what? Now the change in pressure is what? Is fixed. In the case of isochoric, the change in volume or the volume is what? Is fixed. But in the case of adiabatic process, in adiabatic process, these are processes in which no heat can flow into or out of the what? Or out of the what? System. Exactly. And on that note, we can then have that for adiabatic process, the dq is equal to what now? 0. All right. Another major aspect we have to talk on right now is summary of some of the major signs and convention that must be understood when dishing or when talking about this aspect. Now, the first one is what we call heat flowing into the system. Second one is heat flowing out of the system. Now, when heat is flowing into the system, Q will become what? Positive. But when heat flows out of the system, Q is what now? Negative. Exactly. And this aspect also talk about what we call the work done. Now, work done in the system is positive, meaning the work done in the system is positive. But the work done by the system is what now? Is negative. So it therefore means that in the case of heat flow, when it flows into the system, he said that it is positive. So it means that work done by this, that the work done on the system and the heat flows into the system, both of them takes what now? Positive sign. For this one, we said that heat flows into what now? Into the system. It flows into the system. But in the case of this one, of it flowing out of the system, this one is it flows out of the system. While in the case of the work done, when work is done on the system, this one is work done on the system. Right? In the next one, work done by the system. Now, your understanding of this terminology will help us in our next area that we are to enter, which will talk about the pressure volume work. All right. All right, we'll continue on our work. Now, you can see right here on this board is what we call the pressure volume work. Now, based on the pressure volume work, we'll be doing some derivation, a little bit of derivation that should put you in check. Now, you are aware that work is the force times distance. So we can choose to use D or L, but for our work's sake, we'll make it of what? L. Now, if work is equal to force times distance, and you are aware that from the pressure, from the definition of pressure, that pressure is what? Is force per area. So it therefore means that I can now say that my force is not equal to what now? That my force is not equal to my pressure, and that pressure is an external pressure. Take note. So external pressure times your work now times your area. So it therefore means that if I'm to make use of this formula, which is work, I can then say that my work done is not equal to what now? It's not equal to my pressure, which is my external pressure, multiplied by my what? Area, times my what now? Times my length. And you are aware that area and length is the same thing as volume. and that these values are what now? They are change of state. So therefore, I can therefore say that my work done is equal to what now? Is equal to my standard pressure times change in what now? Volume. Because change of volume is a state function, and that the change of volume increase in volume of the what now? Of the gas. And we have to understand some basic facts, that the unit for pressure, that you are aware that the unit for pressure is in atm, while that of the volume is what now? In liters. So we must know how to convert. So it will be interesting to know that 1 liter atm is equal to what now? It's equal to 101.3 what? Joule. So this is part of the conversion factor that we're working on, and based on that, we'll be solving some questions here. Now, a question reads here. The question says, calculate the work done when 4 moles of nitrogen expand isothermally in a constant temperature, isothermally from 15 to 50 dm cube against a constant what? Pressure of 1 liter at 25 degrees Celsius. Now, for to make it the formula, we bring out what we were given. First of all, you were given your what now? Your N. Okay, pause. On the board is said calculate work done. Meaning calculate work done, heat absorbed, and change in internal energy when 4 moles of nitrogen expand isothermally and reversibly at 25 degrees Celsius from 15 to 50 cubic or decimeter. Now, there are 2 major equations we use in solving such question, which is the maximum work done. Now, we make it of nRT ln V2 over V1, or maximum energy is equal to nRT when you are not giving pressure in place of volume. It becomes nRT ln P1 over what? P2. And you are aware that ln x is also equal to 2.303 log x. So in such a question now, let's make it of this formula, which says 2.303 nRT log V2 over what? V1. It's very simple. So you just plug in all your values and the answer will just come outside, which now become equal to 2.303 times, we're given the number of moles to be what? 4 moles. So here is 4 multiplied by gas constant, which is 8.314, which R is a gas constant, which you have to make use of even when you're not giving a question that you are solving, but you should know it, that is a gas constant. And because we want to get our answer in kilojoule, we have to get our answer in calories, we make use of a constant which is 1.98. So here becomes times the temperature given to us was 25 degrees Celsius, which will convert to Kelvin to become 298. So here becomes 298 log V2 is 50, while my V1 now is what now? My V1 is 15. Now, in solving this question out, we should get our final answer to be 11923. 11923. 11923.9 watt now, 0.95 joule. Is that clear? This is our answer. Now again too, we can also get our answer in kilojoule by just saying 11.9 kilojoule. And the second question now says what now? It says calculate the heat absorbed. Now the heat absorbed during the expansion is the same thing as what now? The maximum work done. So therefore I can say that for the question which is the heat absorbed, it is W max, which is Wm, is equal to 11.9 watts kilojoule. Now the next question, which is what now? The change in internal energy. Now take note, since there is no change in temperature, the change in internal energy will be equal to what? 0, because there is no change in temperature. And you observe the statement they said isothermally. Now move to the next area, which was about what now? Which was about what is an internal energy. Now, it will be interesting to know that for real gases, the change in internal energy is not always equal to what now? To zero. And under isothermal condition, because even with T constant, which is even when the temperature is constant, there is a change in internal energy due to change in volume or what now, or pressure. So this answer the question. So therefore, we can say that change in internal energy is equal to what? Zero, because there is no change in what now? In temperature. All right. Now we're going to be working on a very interesting aspect right now, which talks about what we call the internal what? Energy. Now, what is internal energy? Now, internal energy is the total of all the possible kinds of energy of a system. And we can use the symbol capital letter U or E to represent what now? Internal energy. And take note that internal energy is a state function. That is to say, if I have change in energy, it will be equal to what now? The internal energy final minus the internal energy, like energy was initial. Exactly. Now, it will be interesting to know that the energy, it is from here we can now state the first law of what? Thermodynamics. Now, generally, we can state the first law of thermodynamics to be the energy of the universe. To be what now? To be constant, meaning the energy of the universe is constant. We want to state the what now? The first law of thermodynamics generally. But more specifically, we can state it to be that it is that energy that cannot be created, or it states that energy cannot be created nor destroyed. It can only be transferred from one place to another, or it can be transformed from one form to another. And from the first law of thermodynamics, we can have that the change in energy, which is the internal energy, is equal to Q minus what now? W. Now you are aware that change in its limit or change in what now? Energy or internal what? Energy. Why? The Q is the amount of energy that is being what? Supplied to the system. While W is the work done by the system. Remember we said that for the work done by a system, it is negative. While the amount of it supplied to the system or into the system is what now? Is positive. Now we can apply this first law of thermodynamics to most aspects, or to some of the processes that we have in what now? In chemistry. Now take note, for cyclic process involving isothermal expansion of an ideal gas, know that delta E will be equal to 0. And if delta E is equal to 0, so it therefore means that my Q will now be equal to what now? W. Because if delta E is equal to 0, this minus W will come to this other side to mean that Q is equal to what now? W. Now for isochoric process, in the case of isochoric process where the volume is kept constant, if the volume is kept constant, we will therefore have that our change in E is equal to what now? Q, which is QV, which is for isochoric process, telling you that if our V is constant, which is 0, then it will cancel this W out to give out that delta E is equal to what now? The amount of E that is being supplied into what? The system. While in the case of adiabatic what now? Process, there is no change in heat gain or loss, and therefore Q is equal to what now? 0. And if Q is equal to 0, it therefore means that my delta E will be equal to what now? Minus what now? Minus what? W, which is the work done. Now, some questions can be asked under this first law of thermodynamics, which is very, very simple for us to address. Now, we're going to be taking some few questions that we'll use to round up this our first class for today. All right. What I will work on now is the questions, the lastly said find the internal energy Q and W if 2 moles of hydrogen at 3 atm pressure expand isothermally at 50 degrees Celsius and reversibly to pressure of what now? Of 1 atm. Now, since the operation solution now, so since the operation they said it was done isothermally and the gas is ideal, so it therefore means that we start wasting time that our change in E, which is internal energy, is equal to what? 0. And if that is so, you are aware that from change in E is equal to Q minus W, if change in E is equal to 0, it therefore means that my Q is equal to what now? W. Now, if I have to work with the formula that says W is equal to what now? Which is minus 2.303 for reversible process. That's nRT log P1 over P2. We therefore have that minus 2.303. My number of moles there I was giving was 2 times. Because I want to get my answer in calories, so I'll make use of my arrow to be in 1.98 times. Now, for the temperature, so we're going to convert this our temperature that we have from 50 degrees Celsius to what now? To 273. And if that is done, we have that 0 plus 3, which is 3. Okay, 13. That's 5 plus 3 is 13. So here becomes 3. Then the one is that's 3 Kelvin. So I will now have here to be my 3 log my P1, which is the first pressure, is 3. And my second pressure, which is P2, is 1. Now, when we tend to multiply everything that we have here, we tend to get our answer to be what? 1410 calories, which is minus. Now, because we know that our W is minus 1410 cal and that Q is equal to W, so it also means that my Q will also be what now? Minus 1410 cal. So that is the final answer to the question that we have here on the board. Now, I just want to please, if you have not subscribed to my YouTube channel, please do so and share to your friends. Thank you. Till we meet again in our next class. God bless you. I remain Adrenaline. God bless you.